Okay, so you are in ENM2, right? So I think I know most of you. Everyone here took fluids last semester? Almost? Or computational recently? Okay. I sent out an email. Oops, I moved my thing. If your name's not here, that's bad. If you're late, that's bad. Okay. This is your last. Raise your hand if this is your last year.
I hope so.
Okay. Well, let's find out, right? So you will be taking possibly 2 of the hardest classes you've had, right? You'll take ENM2, and you're probably taking quantum. Is that correct? I'm gonna need this as a fireway. Oh, shit. Yeah, no, literally. I'm gonna be over here, right? And we're gonna use boards. Oh. Okay. And we're gonna use this only probably on the first day to demonstrate what you need to be doing to prepare for this class. Okay, we're gonna do ungrading again.
Okay.
Some of the feedback that I got for ungrading is that folks were like, well, you know, I wasn't really motivated to do the homework despite it there being a due date at the top of every assignment. Okay, so I'm gonna go ahead and say that's a you problem, right? But there's an action for me, right? Because there's something I can do about it. So I understand, right? Sometimes folks need to be sort of like worked through things. So I'm gonna add this. Okay, when you turn in your homework, you will get a stamp on it demonstrating that you did it. Okay, if you don't have the stamp, it won't be considered at the end of the semester, right? That'll be like a 0, regardless of whether you turn it in later. Because during our help sessions, I will go over the solutions. Okay, so every week we'll have a help session, and every week you'll turn in work. Okay, one of the things that's really important to keep in mind about the content that we're about to talk about, which is ENM. Okay, anyone have a intuitive feeling for like fluids, for water? Kind of, maybe. People have an intuitive feeling. If I throw you a ball, you know how to catch it.
Yeah.
Okay. If I throw you an electron, what happens? Right. Fuck all. Right. Okay. So it's really important to remember that we're going to do 2 things here. We're going to build a conceptual understanding of one of the most prevalent forms of physics. But in order to do that conceptual understanding, you will have to do the math. Okay. If your attempts are, well, if I just turn in the homework with all the algebra done, you won't understand it. Because you need to be able to use the math to understand the concepts. And so what we'll do in this class, we'll present a lot of really disgusting math that I'm not excited to have to do. And I'm hoping that it'll underpin some really fascinating concepts that describe the most fundamental nature of the world around us. Okay. I also don't know how fast we'll go. Because I've never taught this class before to you. And so that means that I have a schedule here that is kind of a joke. Did you look at the schedule already?
Yeah.
Yeah, good job, Michelle. Okay, so there's nothing on the schedule. And I think this is just me trying to figure out what we're going to do. So we're going to start with a review, okay, today and on Tuesday. And this is really because I'm assuming that you all did very well in ENM1, but that you forgot it all. Right? That's summer, right? The summer gets hot, you bake out all the information. You got to go in the file cabinet, you got to reach back in and get it all out.
Yep.
Okay. Every class, we will do problems in class. And we won't finish the problems. Okay, what's important is not knowing how to do an integral. In fact, most computers can do integrals. In fact, we showed you how computers can do your integrals for you, right? But how do you know where the fuck to start? That's the major question. Understanding how to set up the problem, what to be using, right? Understanding where the symmetries are, these types of issues are what we're going to focus on for this work, okay? Questions? We'll have chickens. They'll give you a grade. You'll do good. Because you're going to work.
Yep.
You're not going to put off homework.
Nope.
And get tons of zeros.
No.
Okay. Yeah.
You have midterms and exams or no?
There will be check-ins. There will be mid check-ins. And there'll be final check-ins. You make it ask that question for you? Back to the class. All right. Okay. The book we're using is here. Everyone have this book? Or a PDF version of it? You found
one we use.
what book found on the internet?
The second edition, right?
It doesn't matter.
Okay.
You have fourth? Okay.
Yeah.
Right. If you get the 4th edition, you get the 3rd edition, you get the 1st edition. I think they're the same, right? Remember that ENM was discovered a A long time ago. Is it updated recently? No. Charge of the electron change? No. Vector dynamics change? Not for many millennia. Okay? Or at least compared to your lifetime. All right. Let's All right. Let's see if this works. Oh. Oh. All right. So I'm going to, everyone knows here that I'm a very good drawer, right?
Yeah.
Super good drawer. So that's going to be really easy for us as we go through the process of learning about these really complicated phenomena, right? So you're going to give me a little latitude. I'm going to give you a little latitude. Okay. All right. When you think about electromagnetism, you stick these two words together, but really they are two different concepts, right? Or at least they seem to be two different concepts. When you think about electrons, you think about electricity. If these words go together, and if you think about electronic music, okay, one of them is not like the other. What is the force when we're thinking about electronic interactions? Sure. Is that a force? Can you write it on the word? Let's write it F. What?
Times E.
Q times E. Okay. What's E?
E is the electric field.
Okay. And what's Q?
The charge.
Good. And what's the way to show E? For say a single point charge, like an electron.
Yeah.
Q.
Q. Yeah, like the absolute value, I think, of both two different Qs. I'm sorry.
Why would it be the absolute value?
Because I thought it was like you determined like the direction.
That's right. You do
Yeah.
determine the direction. So if I have a positive and a negative charge, what happens? A positive and a negative charge go away from each other?
Or the positive.
Right. And why is that? So let's look at this here. Okay. So assume Q is plus and this other Q is negative. Okay. Anything else that we have to add here? Distance, where's the distance?
It's on the bottom. R squared.
R cubed or R squared? Which one?
Yeah.
Okay. Is that right?
There's something else.
Yeah, there's some garbage.
There's a K constant.
Yeah, we won't use K. Come on now.
Okay,
What is this?
4, 5, 9, yeah.
Okay. All right, what is this called? Good. Whose force?
Oh, Coulomb.
Coulomb. Very good. And what's the force quantity, the charge quantity? Usually? Coulomb. It's very good. Okay, so we figured it all out. Okay. So the important thing that we're keeping in mind here is, okay, this is how you compute the magnitude of the force. What's missing? What? Direction, because this is a vector quantity, right? Good. So what's the direction? Radial. Very good. Okay. So let's do that. And you said R cubed. You could do this as well with an R cubed in the bottom and an R in the top, right? Okay. Let's look at this shape though now. If this is directed radially, if I have a particle here and a particle here, and this one's plus and this one's negative, what does that look like? How does the force look? Inward.
Yeah.
Why? Because this is R, right? And that would be minus R. And if they're the same, so they're both negative. Right. Negative times negative is in the same direction. Okay. All right. So you get this one. Makes perfect sense. Okay. I'm sorry, I don't know you. What's that? Okay. Did you take ENM1? Okay. My name is Dr. Grzmani. We did a little introduction at the beginning. Do you want to tell everyone what your major is and your preferred pronouns?
Sure.
Yeah.
A mathematician with focus on physics.
Okay.
Um,
Cool. Preferred pronouns?
oh,
Him?
yeah.
Okay, cool. We can go a little bit over the stuff that we said at the beginning at the end. So that's okay.
No, no.
All right. Okay, so we have the Coulomb force. Right? Okay, you found something in here called E. What is that? Yeah, what does that mean? I don't have an intuitive sense for what an electric field is.
It's like radially outward from like the origin.
Not the shape. That's good though, correct. Not the shape, but what does it mean?
Oh,
Yeah, there's like a potential difference that's occurring, and so then like, you'll have like a tendency of where the charge is going.
Okay, we're tendency where the charge is going, I like more than the first one.
Okay.
Because is this a potential?
No.
No.
So,
Right? It's a force field, not a potential field. And there is a difference between the two, right? There's a potential gravitational field and there's a potential, there's a force gravitational field, right? Okay. Okay, so let's draw some examples here. Here's our, and remember, I'm a very good drawer, so we're going to give me all of them fit out. What do the field lines look like?
I'm trying.
Closest to me taps. Okay, good one. Good. Complicated one. Was that it? Sure. Nope, keep going. Good. Yeah, I like those ones. What else? Keep going. Yeah, okay. What else? One more. Okay, anything else? Sure. Is there anything else?
Errors.
Are there ones, let me ask you this question, are there ones that go like this to infinity? Yeah? Okay. So where's the direction here?
Plus.
They're all towards the plus?
Yes.
The argument is that they're all like this?
Oh, wait.
Raise your hand for all like that?
It's like non-conventional.
That's non-conventional, correct. In fact, that's the opposite of what this definition states. Okay, so we're not gonna do that. Okay, we're gonna do it like this. Okay, they go away from the plus. Yeah, that was very good. Yeah, you took it. You saw your shot, you took it. Coin flip, wrong. All right. So this is the field. Okay. And I heard before that it's just radial. So it's not radial. So why did Rolando get it wrong?
When I originally said that, I only assumed that there was like 1 point charge.
Right. So he didn't get it wrong. Right. So this is a superposition of two fields. And in fact, fields add. Perfect. Okay, so field lines begin on positive, they end on negative, and what causes fields? Electric charge. Charge. Good. So we already showed that electric fields add. Okay, so I could say something like the E total is equal to E1 plus E2. Right? And it'll be chill because these are vector quantities. So in fact, this one, right, would look like this. Here's a plus. And this one is a negative. Let's imagine that I'm really good at drawing these and they're all axisymmetric. Shit, let's not do this wrong. Okay, and then I add those to get that. Can you see it? Okay, here's where you see it. This one goes to that one. Nice. This one and this one bend. Right? So it pulls it down. This one, let's imagine this goes. This one's going up. This one's going down. But these ones on the sides are pulling them over. Okay. All right. So there's two things we can measure about this. Okay, these are going to give us, we have 4 Maxwell equations. We remember them? You just took fluids. So I know you know all of these scalar operators, vector operators, and we're going to learn them intuitively. Okay. What are the things we can measure about this vector flow?
You need like the Dell operation.
The Dell operators, right? We love some Dell operators. In fact, this is the first one. Does that look familiar?
Yeah.
What is that?
I think that's divergent.
That's the divergence. And what does that mean?
How, measure how the electrical spreads out.
How much spreading it's doing, right? Okay. What's it equal to? No. If it was 0, we'd be in trouble. Everything around us would be dead.
The charge over.
The charge
Epsilon?
over epsilon. Okay, I'm gonna be a little specific here though. It's not quite the charge. It's the charge density over epsilon. Good, very nice. So this is caused by sources and sinks. And we're gonna come to Gauss's law in a few seconds to discuss what the integral interpretation of this is. But let's remember, when we're thinking about a fluid, and I'm gonna use a lot of these analogies because I need you to draw on your analogies of something that we intuitively understand, like water coming out of a hose, to understand something that we don't have any intuition for, which are charged particles. Okay. So if I have a hose, okay, and I turn it on, what happens? Water flows out. And I put my thumb over it. I spray my little sister, right? Okay. So that's like this, right? Water is coming out of the hose. Maybe you're my kid sister, and I'm doing like this, and the water is coming out like that, right? Okay. So there's a source that's emanating out these field lines, and the source of the field lines is the charge. That's what this says. Okay. You see that? All right. What's the second thing you can measure? What?
Sink.
This is the sink.
Oh, yeah.
That's where they go. This is the opposite hose. Somehow sucking the water into this hose. Yeah, she's not. The very small hose. Okay. So good. We have the sources and sinks. That's encapsulated in div.e. What are the other things we measure? The swirliness, correct. And that's called curl or yeah, how do I write it?
Yeah.
Oh, del cross, very good. There we go. Sorry, folks. Okay, and what's that? 0. So there's no swirliness? Oh no. All right, and let's remember these are vector quantities, because I'm not very good at that. All right. I will make mistakes. Your responsibility is not to seek everything that I say blindly, but to say, hey, it's this one. Okay. All right. So what does this measure? Curliness. I don't even know if that means anything to me. I like that hand motion. What is that doing? What are you doing there?
There's like the curl of it, so it's like, so my fingers are actually like kind of like active, like how it's like swirling around and some active. That's what I was trying to.
Okay.
Is it describing when there is motion? Like motion of a charge?
I don't see anything about charges here.
Rotation.
There is a conversation about rotation here, right? If we're thinking back to fluids and we say del cross V, that was what?
That was
It was the vorticity. That was a measure of how swirly the fluid was, right? And this is apparently saying there is no swirliness in the electric field.
Oh, did you do the lunch?
Oh, okay. Maybe this is saying something fundamental about the structure of the field, right? So in particular, this says there's a shear or a bending in the field, right? This is what we're going to describe. Okay. So since E adds no curl ever, you get to state really fun statements like this. You just made this point. Well, let's cross it. Right? Del cross E tote is equal to del cross E1 plus del cross E2. Is the cross commutative like this? Better. Better will be. Like this?
Oh, I'm sorry, I thought, I'm thinking something else. Yeah, you're fine.
This should be, right? Okay, good. And this answer is? 0 plus 0, right? All right. Making sure people are awake. You know, I only see 1 coffee in this whole room and it's not mine. 2 coffees. Sorry. Okay. So these are the first 2 Maxwell equations. Okay. Is there, so we talked about electric charges. Example of an electric charge that's negative is the electron, very good. And the electron has what charge? Yeah, -1.
Yeah.
Right, it's the most fundamental charge unit. Okay, what about this one? What about plus? Are there plus electrons? There are positrons. Are they found commonly? No. What's our what do you tend to think about when we think about a positive charge?
A proton.
A proton, right? And that can either be in an atom, or it can be a single proton. That would be hydrogen if they got together and they had friends. Okay. What about magnets? How do they work?
They have a positive.
What?
They have like a positive and a negative end.
They have a positive and a negative end.
Yeah.
So you're telling me something like this?
Yes.
I know that's really well written. Is that true?
Yes.
What?
I said that could be true.
That could be true. I thought you wrote it, but say, oh, I'm not gonna commit to that. Okay, so you're telling me, so if I take this though, and let's say I like cut it in half. Okay, I'm gonna use a saw. Really good drawing with saw. Right? Saw it in half. And I put this piece over here. Okay, now what does it look like? Is it all south?
No.
Oh, what happens? My beautiful magnet's all broken. What happened? What does it feel like?
It's polarized.
Polarized? I haven't talked about polarization. You've never even learned about polarization. Okay. Don't introduce the concept. This is magnetized. Magnetized and polarized are different, right? Okay. But this material is magnetized. Why is the material magnetized? And don't say because it's ferromagnetic. That's cheating. What gives objects magnetism?
I'm gonna say charge.
Why a charge?
Oh, I know with magnetic fields, you need like some sort of charge, but then also some sort of velocity associated with them, or that we're moving.
Okay. I'm gonna hold on to that idea. I think you're in the right region. Let's make sure we use our words very carefully, because this is a weird concept.
Okay.
Is there a magnetic charge? Is it in the room with us or not? Is there one magnetic charge? Or a particle like we just talked about here? An electron?
Just charge.
There's just what?
Oh, wait.
I think you can describe a force in terms of magnetism.
We will write forces in terms of magnetism. That's not my question. My question is there a particle responsible for magnetism? No. Is that weird? Yes, it is weird. You should be confused, right? The reason why magnets don't make any fucking sense is because every single atom has electrons that are moving, right? Those electrons moving generate magnetic fields. So the electron is still at fault, but there is no magnetic monopole. And we write that very simply. We write that as, well, let's write this slightly differently. Hold on, I got out of order here. Oh boy, where's my notes? Here we go. Very good. Okay, so I can never make this picture. Right? I'm all, oh, it's okay. We're gonna be fine. What's the other one? What's this one? Cross. Yeah, what is that? It has like a number? No.
No.
What causes magnetic fields?
Motion.
Motion and charge are both right, but you need to add your thoughts together.
Uh,
Motion charge, good. And motion charge is called? And the lights are on due to motion charge. What?
is it current?
Yeah, so energy is important, but current is the word I'm looking for.
Two to go out church.
That's okay. Relax, okay?
So that's current sense.
Yeah, I don't really like the letters that we're gonna end up having to use here.
Yeah.
This is current density. Annoyingly, right? This is the, yeah, it's a J. Sorry. My God, all right. All right, this is current density. What's this?
Oh, J over A or something.
This is a line density.
Oh, okay.
What's this? Surface density, very good, you figured it out. Alright. Okay, do you see the problem that I have with this notation?
Yeah.
As I increase in dimensionality, I go I, K, J. Is that reasonable? No, but we're stuck with it. Thank you, people in the past. Appreciate that. Okay. Okay, so now we have our first two Maxwell equations. So let's think about this in context. I'm gonna get rid of some of this, if that's okay. Okay. Let's move a charge. Okay. Have a Q. Say this one, and we're gonna move it at constant velocity. Okay. What happens? Magnetic field is generated. Good. Okay. So we say that in the terms of this, right? We say that there is a magnetic force. Seen that before? And what does that look like?
I think it's Q parentheses. V velocity times magnetic field plus any external. Oh, V plus.
Yeah. Yep.
All right. So magnetic fields suck because of this cross. They're very unintuitive. They don't do what you want them to do. But generally speaking, and we'll see some analogies to this, they act like rubber bands. So I'll try to continue to use analogies to help you understand, but they will always break down because nothing is quite like, okay. Okay. And what's F total? Let's imagine the force on this little baby electron or something nearby.
And both of those ideas together.
Very good, very good. So take that one, take this one, we're gonna smush. Okay. And that's what?
Q quantity E plus V cross V.
Okay. And you're not gonna see this on one of those like Twitter PEDMAS arguments, right? You ever seen one of those? Is it 15 or is it 6? Right? Was parentheses come first? So which comes first in here? Oh, V times B, correct. So that's one quantity, and this is another quantity. And you're never gonna do E plus V, right? Just make sure. All right. Okay, so generally speaking, let's imagine a wire. Okay. Let's put some current in it. Okay. Imagine it's going up. What's a magnetic field look like? Good, I see almost everyone's hands. Okay, so what is it in here? Out or in? In. And we like this symbol?
Yep.
Okay. You familiar with this? This is the arrow. Okay, and on this side? Good. So this is the arrowhead coming at your face. Right. Okay. So now let's put another wire. Okay, the force felt by this wire is what? Write it down for yourself. Tell me. Which direction? This way? This way? This way? Or this way? Or some other way that I didn't write. Come on, hey. Raise your hand if you got it already. Raise your hand if you need 5 more minutes. Raise your hand if you need 1 more minute. Raise your hand if you don't want to do it. Not enough hands. Okay, so let's work through this together.
I started with the right hand rule,
You just started with right hand. What does that mean?
so I use. So you have to use your right hand, obviously.
No. I know. Okay, I know what the right hand rule is. Don't get me wrong. That's fine. But how did you know that you need to start with the right hand rule? What about this problem told you right hand rule?
Curls.
Incorrect. What is curls? Because of one more step. One more step. Why did you know to use a cross product?
So we look forward.
Because there's magnetic field, right? I want you to walk through every step here. When I see your homework and the first thing you write down is this equation, you will get no credit. Because anyone can write this equation down. Understanding or demonstrating where to start is the most important part. Because as you will learn, these 4 equations govern all of electromagnetism. Which one did you pick and why? That is the most important part. Okay, so let's go back to your point. So you said, oh, cross product. Great.
Yeah.
Maybe I wouldn't have seen that right away, right? So now it helps for me to see, oh, you chose the right hand rule because you saw this cross product, because you saw the B.
Yeah.
Good. I don't see an I. Anyone worry about that? Okay, good. I know the B. I see the B in the problem. What am I gonna do?
Don't worry about that.
Just what is I?
It's that current.
The motion of the electron. So in fact, I do have Q and V, because that's what these things mean. This is the motion V of the electrons Q. Okay, so I is hidden in here. Okay, so now let's do the right hand rule. Go ahead, Rolanda.
So I used thumb for the V for the velocity.
Okay, thumb for the V or maybe the I. I'll take both of them. Good.
And then I know that it's going into the board, so I use my index finger to put inwards.
No, sorry, which one are you calculating? Are you calculating the force on this from this, or the force on this from this?
No.
Because I'm asking for this, let's call this wire 1. Let's call this wire 2.
Oh, I see.
I want the force of 2 from 1. What is 2 feeling? How's 2 doing?
That's too sick.
Makes sense?
Is the arrow indicating the direction of the current?
Yes, yeah, sorry, these are the directions. The wires don't typically have arrows on them.
Okay.
Let's do it like this. Right?
Oh, okay.
Okay, Isabel, do you want us to walk us through this one?
I just of 1 on 2, if you take the velocity of 1 or the velocity of 2,
Good question, yeah. What do we do?
how many this?
So yeah, you have another 50% chance. You just flip that coin, you hope you get it on the homework, right? How do you know?
I just
Okay, so she's saying that I is down for wire 2. People agree? Because I want the force on I2. So I want to feel this Q here is the one that's doing the motion, right? Just like when I throw a ball, okay? the force that's on the ball is the mass of the ball and the acceleration of the ball. So this would be the current of the wire considered and the magnetic field that it is experiencing. So in that particular case, the direction here shows us I is down, B is where? Into the board, good. And therefore,
Of course, that's being done.
good. Can you see it? Okay, everyone can do that, right? No? Yes? All right, let's switch it. Parallel wires. I'm going in the same direction. Now what is the force direction? Toby already has it. Why?
The right hand rule again.
Well, you show me. How do you do that? Show me with your hand. Not up on the board, but just show me with your hand.
See if I going up,
I going up.
magnetic field going into the board,
Magnetic field going into the board.
then you have forces effect.
Force them. Okay, so we'll practice these, right? We'll get really good at them. We'll just rattle them right off. We'll never get them wrong ever again. Right? Okay. What are people's, raise your hand if you're planning to go to grad. Raise your hand if you are planning to go to industry. Raise your hand if you've never given a thought to what you're going to be doing in a year. Just me? Okay, good. So one of the things that we're thinking about, as you know, I'm going to go through this process. We're going to review some material. I'm actually going to hand you your final, and you're going to do parts of your final with me so that I can understand where you're at. And then we're going to do some weird stuff in this class because I like to teach things in a different way. I don't particularly give a shit about magnetostatics and matter or electrostatics and matter. I think that's stupid, but you have to learn it. And so we will learn it, but we will spend less time than you might learn in, say, Dr. Woodney's class or PK's class, right? Because they have a different interest in the material. I like light, okay? I think that the more that we learn about light, the more valuable that is for your career. But if you're, saying, hey, listen, I really need to understand this magnetostatic stuff because I'm going to go and be an electrical engineer and design circuits or something, right? Just stop me, let me know. We can spend some more time on any of that material. Okay. Generally speaking, it's just like a lot of new letters for the same concepts, right? Instead of B, you have like H's and D's and stuff. It's like, okay. Polarization, great. Polarization of molecules, cool. Everything else bad. Okay. That makes sense? Okay. Okay. So we said that J comes from moving charge. We want to understand these two here, and then we're going to do a small break for one problem. So we're going to set up, we're going to show how the homework will work. We'll come back to material. Let's look at a box. I want to understand this one here. Okay. Okay. So that's my box. Let's imagine that out of the different surfaces, J is coming out. Okay, so if there's more going out than coming in, then I would say this quite simply. Okay, I would say something like this. Now, I know it's been a while since you saw this. Is this freaky? No, what is this? Yes, that's 100% correct. As always, correct. That's not what I'm asking. What does it mean? What have I shown you? Yeah.
How much dense, how much is losing over time? How much density is losing over time?
How much density has been lost over time? Good. And what kind of equation is this? We saw this last semester. I told you we'd make analogies.
Yeah.
Well, you're not to forget anything in fluids. Baked it right out with that summer sun.
Are we thinking about an analogy to describe that?
I'm thinking about a word. This is the name of an equation. Right?
Oh, okay.
What is this thing?
There we go.
What is that?
Hang on, that kind of helps.
Imagine it's not charged, imagine it's fluid coming out of the box. Flux. There is a flux, this is definitely the flux of something, and we'll talk about those when we talk about Gauss's law. These have to do with fluxes, okay, we'll talk about that, these are the Stokes theorem. There's a lot of analogies, we're gonna have to remember everything that we forgot, okay? This, if we imagine J is not J, but it's water, and this is a box, and there's water coming out of the box. The density in the box goes down. That is the continuity equation.
Yeah, dang it.
Right? Oh, forget about it. Okay, so now we find out there's this really beautiful parallel. So as charge moves out of the box, right, with time, there's divergence. Okay? Let's remove this analogy so it doesn't confuse people. Okay, and then let's say we have some balance in this life. Let's do this, let's get rid of this guy. And we're going to reverse this one. Okay. So now I want to know. Now what's del dot J? Now what is del dot J? Is it still this?
You moved the negative sign, so everything was leaving.
Yeah, in the rate of change of the density will be negative the divergence.
Yeah.
Isn't it 0 in this case because?
Yeah, but let's just make sure as well got that for
Oh,
all.
really?
That makes sense?
It does seem weird because with the water, it goes into the box, it gets more dense, but you're saying stuff.
Well, but remember the way that we define divergence is away from the source. That's just by definition. If you wanted to take del dot and switch negative del dot, then you're absolutely right, right? But even when we wrote it in the water, we said negative d rho dt. That makes sense? Okay, sorry, your point? Yeah, go ahead.
Is it like, so the arrow, the J going this way up to the right, is it like it's leaving and there's a J is coming in?
Yeah.
So the equal-
Yeah, so they equal each other. So therefore, this side is 0, right? When they're balanced, no net change in the charge density. So J comes in, J goes out, so this is 0. Okay. So this thing here is what you study. That's magnetostatics. That's even more boring. Okay. What we'll study this semester is the cool one. When charge is changing. Okay. Charge is changing, it leads to fun things. So just like we observed this bad boy over here, this was what again? Whose law was this? Coulomb. How'd they find it? Went on high, passed down this bronze tablet? Yeah.
They ripped off like.
No. No, this is not a remix. Anyone know the history of how this was discovered?
Like,
Yeah, that would make a lot of sense. In fact, this was discovered in the lab. So what you would do is you would take 2 shiny little orbs and you charge them up. You hold them on very delicate strings and you see how much the strings were bent. Okay, you move those orbs closer and farther and you could test these different pieces.
are you talking about light bulbs or what kind of?
No, like literally think a metal orb that you would find in Skyrim. It's perfectly spherical orb. Okay, and then you have to charge it up good.
It's like that one that's downstairs, the thing with like the string.
I don't know when that is.
Robot.
Earl brought it?
Oh.
Maybe.
I think it was just a conductor.
Was it?
Yeah, it's a conductor, right? You want a conductor so you can put charge on it. You want it on a light string so that the string doesn't influence the observation. And then you move them at different distances and you see how bent they are. You measure the force, right? You compare it to gravity. So this is empirical. No one just dreamt it up one day. They saw it. They saw it in a lab. Okay, that's fucking wild, first of all. Second part, they did it with magnetism. Okay, so they did, what's the, can I get rid of? I need like 3 times as much white space. I mean, there is. I need it though, Aaron, I can't. It's part of my soul just died. Well, it's no, I may have to, and I certainly will get the other truck, but do you see this truck? Oh, yeah, it's the bane of my absolute existence because it just snaps to a million pieces in my hand. Alright, okay, so let's talk about this is everyone's favorite law, right? Because it's got such a cool name. The Biot-Savart law. Everyone remembered this one perfectly, right? Uh-huh. So what am I saying here? What? Oh, you want the spelling? Okay. Intellectually, what have I said? Yeah, okay. Another way of saying it? This is the field, right? So what creates the field? The I. Good. Right? So the stronger I, the stronger B. Good. What else do I have to interpret?
In like the curly rings.
Yeah, there's like a curly bit to it. Good. What?
That sets the direction.
That sets the direction curl to both of these vectors, right? So let's take some curly wire, okay? Oh God. Let's imagine that I knew how to draw a wire. Okay. Now B is defined everywhere. Current is flowing through this wire. Okay. But let's take a random location here. And I want to know the B there. So how do I calculate this? Correct. Good. Very good. Nice stuff. So, but conceptually, what am I going through? You're going to go through the wire. That's what the integral DL is.
Yeah.
And you're going to walk through every little slice. And you're going to see what the contribution is to the B at this point, because they all add. Remember that we talked about E fields adding? We're going to see here the individual contributions of B are going to add up to give us our total B field at a point. The really nice thing, vector field add. Thank God, right? Vector fields didn't add, we really screwed. Now, when we multiply two vector fields together from our choice, then we really screw ourselves, right? That's non-linear phenomenon. What we're talking about right here is the linear contribution of all of the current in this wire to what the B field will be at this point. All right, so let's look at that. If you're far away, you'll contribute less, right? That's the 1 over R squared. The current's higher in a certain point, you'll contribute more. The direction is curly. So here, as I'm rotating around, okay, contribution over here is, let's look at it, yes, like that. So what's the contribution from this point here? Let's do 1 point here, 1 point here, and 1 point here.
With respect to
With respect to the point B,
one.
1 is into the board because it's on the left-hand side, right? And it's above. Good. 2 is out of the board. Good. And 3 also out. Right? So different pieces of the wire contribute either plus or negative because of the cross product. Okay, and we love this one. Super easy to use, right? Yeah. Good. Okay. Okay, so this one here says that there's no magnetic monopoles. We can see that because when we look at the Gauss's law, we'll see that this is the divergence of B is 0. There's no charges enclosed ever. Can't find a magnetic charge. I keep cutting this magnet over and over. Can't find it. And this one here says that the curl is due to currents. And this is the way that it's due to currents. Currents flow through something, they generate E2s. Okay. So before we all die and fall asleep, okay, we're going to understand how to do problems. Oh, no, Mateo, I hate that though. I don't like learning. Okay. So you may recognize this, and I hope you do. Find a partner. No, that's the exam. Somebody got rid of this thing. So I asked PK, how'd you guys do on the exam? And he said, you know. He said you guys are solid. I wanna make sure that we understand as a group what the expectations will be for the work in class and home. So in particular, what I'm trying to point out here is that we are going to work on problems. We're going to set them up. And we're not gonna do the algebra in class. We're doing the algebra in class, you're gonna have a bed. Okay. So find a partner. I know that there's an odd number here. I apologize. You can put it by yourself. No. You can have one group of three, but usually two. And the problem that you're gonna work on specifically is problem. Is problem 4. Okay, so if you're alone, right, what you're gonna do here, don't start talking about it first. First, look at the problem, see how you would set it up, and then communicate to your partner. Okay, start talking about what you would do, and don't just write down an equation. Talk about why you wrote down the equation, right? Remember when we just jumped over here? Let's not jump. Yeah. No, you're not looking for the answer. You're not looking even for your notes. If you don't know how to do it, just say you don't know how to do it. But I'm trying to understand what you've kept in mind, what you've understood. You're doing problem 4.
Oh.
I wonder why I gave you problem 4. Maybe most of you skipped problem 4. I don't expect you to remember everything, but I do expect you not to look at your past.
Well, don't look at your best.
No, of course not. Well, yeah, use the cheat sheet. I don't expect you to remember the formula, but I do expect you not to use your last answer.
This is.
Yeah. What do you got on there?
I have the problem 4.
Okay, just make sure you're not using an iPad to do anything. Thank you for that.
Yeah, you already used this. You already.
It's written down. It's in your book.
You know, if you went over that when I was from virtual. School instrumental learning pieces and asynchronous. I read some other things that we could do. But I think we're gonna do them. Cause I have to do my full stuff on I literally just gave them that's why I so there might be days that I just won't come.
Oh, and I'm recording.
Okay.
Yeah. Reed's not here either.
Reed's the one who did this problem.
Yeah, Reed's probably.
Okay. Remember, you're not doing the problem, you're setting up the problem. Good, so then talk to your partner. If you don't know where to start, find someone and talk to them. Wait, not all three of you. Just put a couple of there. Friends can't all be friends, you gotta also make new friends. I know, it's crazy, it's crazy.
We're all friends.
These are words.
I want you to use your words. Start with the equation. That's not good.
That's how you do it.
Why two more of you chose word?
Okay.
Velocity, we want to use.
Those two were groups of four. Come on. Too many grounds.
This is all really loud.
We're not talking.
Oh, yeah.
Yeah, you can say because we have charge in motion.
Right? You can like see it, like, yeah, it's like literally almost.
Oh, but you won't need those.
From
No.
those, we can find.
No, those are vector identities. If you use vector identities in class, I'd kill myself. There we go. Nice word. Nice.
What's the initial velocity?
There's no initial velocity, an external E field and,
Yeah.
I think that's kind of.
That's my.
Energy much, yeah, hour.
You know, it was.
Yeah.
4, 5. Times 10. Yeah. Oh, yeah. Yeah. That's like negative.
Oh, yeah, at the beginning is.
No.
Yeah.
Well, yeah, we did that last year.
Probably it's not-
Yeah.
Yeah.
We definitely went through that.
Yeah.
We definitely- I think we did it a little bit different in the sense that, it was like, I think related to a TV. And then we were gaming it through like, and then you see how it bent based off of the field.
That's like, we have to remember that one. Oh, permeability of free space, like electric ones.
yeah, sorry,
Yeah.
we have. We can make
I don't know. I'm just leaving that.
I'm just leaving.
Yeah.
Okay.
Yeah.
This right here.
But still, there's nothing effective. That we have. But we don't have to. Like what? Yeah.
Yeah.
Isn't it like,
Alright.
I'm almost talking about, you have like, when you're talking about charge, you're talking about charge.
Yeah, we charge gas and
Charge.
we don't know the math, in the unknown aspect. Well, we do know the charge. We do the farm.
We could,
Grounding side, we get we get the case, you know, that's. You know, the right hand will define that, but it shouldn't be.
So face this way. And then.
Well, we're trying to find.
You're talking about. Yeah.
Smart idea, right? The final?
Because it's like we're given.
It's evil.
That's evil.
We're given
You're welcome.
directly down, so like.
It makes.
That's saying like, that's where,
Oh, yeah, it'd be like this. Ease directly down, or no, sorry, I meant really directly.
so the charge is gonna want to go down. Right,
No, it's actually the one I'm, so we can take that.
Like snow, remember?
but isn't the electric the same thing, X is only when it's on people.
That is true.
Think of it like rather than going down, like, so if this is a projectile, this would be.
That's true.
But our exit
That-
don't have
that is
it.
rare. I was actually gonna bring this up.
Yeah, there's the.
Because think about it like this.
Only thing is, not yet.
This will, this cross product will have to sum into X method. Okay?
Yeah,
And then this will have to sum into.
if we call that the y, and this is X.
Yeah.
This is Y.
Oh, yeah.
It would be like into or out of the board.
Yeah.
Or you can call it C, I'm saying call it down. Yeah.
So that's.
Yeah, if you based off of this,
Yeah.
because Y would be out of the board. Right, or am I crazy? Well, X would be this way, Y would be that way. Yeah.
Yeah. you would definitely be up there. I thought you would like to-
Oh, okay, then, yeah, sorry.
Yeah.
I would. I think we're trying to do that. So it's gonna look weird, but. So Y is up, X is here, and then B is out.
Yeah,
Based off of like that.
yeah, definitely.
There it is. I mean, it's just hard to describe it. Yeah.
That's how I remember doing that for a second.
Okay,
Oh.
so you were just trying to get down like directly together.
Yeah.
Find like the results of that.
Okay, yeah, you're right. So this is, this is in terms of, I guess, our Y direction. This is in terms of, leading in this direction.
Yeah.
And the curl of it,
Like,
It's
this guy
going-
find something. That's what, at least that's what I remember right now.
you wanna look at it that way. So B cross B, that means that it's gonna be experiencing a force. Is that weird?
Okay, folks. Let's put everything down for a second.
Okay,
Think about the groups that you're in. Okay, you guys a group?
Yeah.
Okay, which one of you wants to explain how you started?
Yeah, but. I mean,
What kind of problem is that?
I mean,
What do you mean? What do you mean? What kind of problem is that?
the magnetic problem.
Okay, there's magnetism, good, and are we looking at wires? Are we looking at individual charges? What are we looking at?
Ions.
An ion, so an individual charge.
Good.
All right, good. All right, this group. What does that tell you from that information? What are you trying to determine? Are you trying to determine the E field, the B field? Are you? Right, so they're both given, so it's not a B or an E finding field, so we don't need these things, right? I deleted them. Okay, so what are we doing instead? This group,
So it's a single particle going in a perfectly straight line. Underneath the first both know that which means that there is no acceleration. Means the force will be zero.
there's no acceleration
There's no change in that. In the first, in zone one,
in zone one, okay, in zone one, it's doing what?
there's no acceleration because, you can see it going from the. It's going in a perfectly straight line. So but with that.
So unfortunately, so this is a tricky part, right? Because then question A is kind of silly. right? What velocity ion V naught will exit zone one? There has to be some acceleration. What's the acceleration due to?
There's no acceleration up or down, they have to
Right.
cancel it out, so.
Alright, there's no in the page or out of the page like this, or like this, but which direction is the acceleration? This way. The E field is down this way. Right? Going that way. B is this way, and they're somehow balanced. Such that you only get it that way. Right? So you're right, the straight line is down. Okay. And then you have a weird thing where the E disappears and you curve. That sucks. Okay. Okay, so what are you using here for this very complicated, super difficult to do?
Is it like a conservation? type of-
It's set magnetic to electric.
Yeah, let's work through it here.
And why do you do it? I didn't know what to do. I just knew, like, they just, you know.
So F is
F equals Q times, or quantity E plus E cross B.
okay. So in zone one. Right?
Yeah.
So in zone one, the X and Y components, right? So X component can be whatever we want it to be, I don't care. But the Y components have to be zero, right? So Y component equals 0. That's the requirement. So that means that I can look at these, I can break these apart piece by piece, and I can set them vector wise. Good. And then the X component will necessarily not be 0, right? Good. Or you can say it this way, let's do it like a computer. Nice. Okay, good. And also that looks bad, I'm sorry. All right, good. So then what happens for 15? Sorry, for B.
Wait, that's for
I'll say,
all you gotta do is just write Y equals 0 and X equals 0.
well, you have to do the rest of the algebra. Remember how we're doing this.
Yeah.
I'm not gonna do algebra this time.
But what would the next step be to that?
Okay, well, you need to write this.
Yeah.
What's V cross B?
Jumbled mess.
Did you say a jumbled mess?
Yeah.
No, X cross.
It's, isn't it, the product of B and B and then whatever angles between them? Right?
Okay, well, if we do this in vector calculus,
Oh, just like, B and B and then like the direction you pick for what you're looking at.
in vector form, right? Because this is
Oh,
E X in the X hat direction
Yeah,
plus E Y in the Y hat direction, right?
yeah.
Okay, and B is B X, right?
Yes,
In the X hat direction,
yes.
and so on and so forth. So what is the cross product?
it's multi-dimensional.
Okay, we're gonna remember how to do cross products. I'm not gonna do them on the board,
Yeah.
okay? But these things are doable. Okay? We're writing down formulas and we're just churning through them, just like we were doing with derivatives and tensors and fluids. You just do the derivatives. Derivatives are the easiest things to do. Cross products, they look annoying, right? But you just get a nice little matrix. You get something up here, you get something down here, you get something over here, you get something over here, and you see that this is BXX, and this is BYY, and this is BXY, and this is BXY, right?
Right.
Remember that? Okay, good. It's all coming back to us. So it was easy. It wasn't easy, but it was straightforward. You all should have gotten perfect points on it, right? Okay, second part, part 2. Zone 2. What? Didn't get that part. What did you guys say? What did you guys say?
You didn't ask for.
No,
What?
we can still find it though.
Oh,
They didn't ask for what?
It didn't ask for something, but we can find it.
We're gonna need to use zone 2 to find it.
Yeah, sorry, I'm hinting to you.
oh,
And I'm telling you already, something special happens with zone 2.
Yeah, no more like.
No more electric field,
Yeah.
okay, but we knew this, right? We had the velocity coming out, right? Now we have B. And what happens to a charged particle in the presence of only a magnetic field? Only spinny boy, right? No speed up boy. Okay, so V stays the same. And now you get gyroscopic motion. Okay, but in particular, we're gonna smash into the side of a wall, so that doesn't matter. Okay, so what do I use here?
Now we can drop,
Now we can drop E, good,
and then just use B cross B,
good.
but we can describe this in terms of acceleration.
Okay, what do you mean acceleration?
We want the centrifugal force.
Centrifugal force, and what does that remind me of? What?
M times V squared over R.
Bada bing, bada boom.
Yeah.
Good. We did it. Okay,
And then we find out.
okay.
Then you solve it.
So I'm going to encourage you to not just, oh, he just did it, I'll never have to think about that again. When you finish, right, remember that there is learning that happens in the classroom. There's learning that happens on your own. And there's learning that happens in the student help sessions, which all of you are going to sign up for your availability so that I can have one that services you, right? Right? Okay. And there's learning in all these places. So we'll revisit the material. So I have a few more minutes, so we're just going to talk very briefly about Gauss's law.
Can you get the key, please?
Yeah, you're gonna keep, well, we're gonna revisit them on Tuesday.
Okay.
So I'm gonna get problem 4 from you at the beginning of Tuesday, and then at the end of the class, I'll get whatever other problem I assign to you.
Problem 4 completed.
Not completed, set up.
Set, okay.
Yeah. What? No. Excuse me, I like it. We don't have homework yet, we're doing a review. If you want to, I encourage you to do all of the problems, right?
All of it, but.
Prepare yourself. You will be learning the hardest level of physics you have encountered.
Yeah.
Okay? Okay. So you should read chapter 1. Review the math. You will need to know that. Not knowing the cross products is not a good sign. Okay? You need to snap into gear quickly. The summer does not go, right? And something goes by so slowly, blah, blah. And then the quarter starts and you're done. Okay? 15 weeks is gonna go a lot faster than you think. Okay. So let's remember 2 fundamental theorems. Okay? The first is Gauss's theorem. And in general, in fluids, we'd like to skip over the math part because the derivation sucks and I don't want to show you. But conceptually, they make a lot of sense. And they relate 2 formalisms. They relate the integral formalism with derivatives. So I have written here del dot E equals rho over epsilon naught. What is a different way of saying this?
You can add some terms to both sides, and then you can also integrate both sides.
Yeah, let's integrate these, right? There's a way of talking about these in forms of integrals. So I said del dot E equals rho over this. And I claimed that I could say that the divergence in this area is due only to the charge. Okay? But another way of saying that is that if I integrate the divergence over a volume, that's a perfect circle volume. Okay? That's going to be same. This will be the same as the vector field integrated along the surface. Okay? So as I walk along, I'm going to measure up all of the things going in or out. Okay, and as I walk along, I'll measure, okay, this is going out, this is going out, this is going out, this is going out, this is going out. And I measure them all up and I say, oh, they're all going out. So therefore I have a positive number. And there's a positive charge. That is Gauss's theorem in a nutshell. I can write it up on the board in a few seconds. Here, I do the same thing. I look at this volume, and in the volume enclosed, I can find out if there's charges in the volume enclosed by walking along the surface and seeing how many lines go in or out. Okay, in, these will be negatives, negative, 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 and I have a negative charge in here. Okay? And here's the tricky part. Let's take a volume here. That's a megavolume. Okay, now let's walk along. As I walk along, shit, which direction are these? We go to the negative, right? Okay, so this one's going in. So let's make in negative. So negative, negative, positive, positive. Those cancel. Now it's 0. Positive, positive. I didn't draw this very good. Positive, negative, negative, negative. How much charge is in this volume? 0. You're like, Matilda, I see 2 charges. No, because charges, they're added, right? They cancel. Okay, so the sum of the charges is 0. So the integral formalism and the derivative formalism are the same. And we'll show that at the beginning of class on Tuesday. Okay. No homework this first week, but you do have personal work. You will sign up for student help sessions. You will respond to my survey. Okay. You will make sure you have the book. You will reread chapter 1. Find out what a cross product is. Be prepared for intense amounts of math quickly. Okay. We will hit the ground running as you saw today. We will not stop until I get tired. Okay. Questions, comments, concerns?